Hello, and welcome to Things You Thought You Didn't Need to Care About That Have a Big Impact on Your Job. And I think that title just shows that naming really is the hardest problem in computer science. I did that name, and then as soon as I saw it written down on the program, I was like, oh no, that's a terrible name. And the second hardest problem in computer science is finding good illustrations for things, although I'm not sure you could actually count that as a computer science problem. I have a picture of a ball of knitting yarn here. We're not actually going to talk about knitting. I have another talk with Trisha G that we did last year at Devox where we do talk about knitting. If you want to know about knitting, I would recommend that talk, not this one. But we're going to talk about everything else, which is perhaps why I had a hard time settling on a single picture. And what I'm really going to talk about today is the invisible forces that shape your job, that maybe don't have anything to do with knitting or with computer science, but still somehow mean that things are different for you. Another way of thinking about what I'm going to talk about today is that I've been programming Java professionally for about 25 years, and this is kind of the aggregation of everything that I know about our industry, which even after 25 years isn't very much, which is why we can fit it into 50 minutes. So I want to start off with the big questions. Why is everything hard? And maybe an even bigger question, why are computers terrible? Hands up if you've felt this when you look at your code. Right? And to answer this question, we can almost go back to university and some of those subjects that we maybe didn't take that have some answers. So in particular, the answer to why everything is terrible comes down to geography. And in particular, it comes down to the existence of Norway. Hands up if you are Norwegian. Oh, darn. Sorry about that. It's all your fault, but I'm sure nobody will hold it against you. The reason Norway makes everything terrible, hands up if you know where this is going. A couple of hands, yes. I have here this very innocent-looking piece of YAML in which I wish to describe places I might want to go to ski. And I could go to France, I could go to Switzerland, I could go to Norway, or I could go to Sweden. I run that through my YAML parser, and what comes out is this. I could go to France, I could go to Switzerland, false, or I could go to Sweden. And the problem is that Norway gets turned into that false. Because when the spec was designed, they said, if someone writes no, they must mean false. They couldn't possibly mean Norway, because they kind of forgot about the existence of Norway. There's all sorts of similar problems that you can do. So for example, if you want to write a list of cricket positions in YAML, I'm not really sure why you would want to write a list of cricket positions in YAML, but if you did, you would have off in your cricket positions, and then that would get turned into false, and so your fielder would be in the false part of the field. It just doesn't work. And this is funny, but it's also quite sad, because it was this really well-intentioned decision, right? It was a sort of a kind decision of, let's make things easier, let's put some assumptions in so that we can, convert that no into false and make everything easier. But it had this really terrible outcome for anybody who wanted to talk about Norway, which was probably particularly the people in Norway. And then this kind of brings a bigger question, which is, if something so apparently okay had this bad impact, how can we know what outcomes our decisions will have? And what that's really asking is, the world is really uncertain. How can we possibly make decisions in such an uncertain world? So this brings us back to our next subject, which is statistics. When we talk about statistics, a lot of us don't really like talking about statistics, but statistics has had a rebrand lately. So what do you call a statistician who lives in San Francisco? This is partly a statistics question, and it's also actually partly a geography question, so we're on to Geography 201. What you call a statistician, or someone who does statistics, because that's easier to say, who lives in San Francisco, is a data scientist. So it's the same skill set, but you rebrand it, and you live in San Francisco, and all of a sudden, your salary is doubled. And so we have this really sort of progression in the field in terms of the skills, but also what we call things. So when we start with statistics, that's really boring. Nobody is cool who does statistics, clearly. But then we can go on to data science. If you do data science, you are cool because you can get a job where you get paid tons of money, so then you can buy cool things to cover the fact that at heart you're a statistician. And then you can go on further and you can go to machine learning. And at that point, you can get a really, really good job and raise lots of venture capital, and then you can eventually do AI. And although these are building on each other, the foundation of all of it is this kind of boring, kind of uncool statistics. You might be able to tell I didn't like statistics in university. I did have to take statistics in university. I hated it. It made no sense. I slept through the entire lecture. I really regret that now, because only after leaving did I realize how much statistics there is everywhere. So had I enjoyed statistics more, I could have become a data scientist and earned tons of money. But even without that career path, statistics is actually really necessary for lots of things, and it's really necessary for understanding the world. So when I think about statistics, I quite often think in terms of, the sort of the statistical significance and standard deviations and that kind of thing. But there's another type of statistics which is probably much more useful if you're not going to do something like publishing a scientific paper. And that's Bayesian analysis. This is named after Thomas Bayes, who was a minister living in the 1700s, and he came up with this equation. When Stephen Hawking did A Brief History of Time, apparently his publisher told him that for every equation he put into the book, it would halve his sales. And I assume it's kind of similar here, right? So for like every equation I have on my slides, I have my speaker ratings. So just to set expectations, we're going to go for quite a few slides with this one, but then there's not going to be any more equations after that. So you can. So what is this saying? It's just like a salad of P's and A's and B's. So when I started reading about Bayes statistics, I saw this and I was like, I don't really understand this, and I'm not sure it helps me very much. What this is trying to say, this is the question. Given A, what is the probability of B? And I'm just looking at my slides now, and I have a horrible feeling that in some of the later slides, I have actually swapped the A and the B, which brings us back to I slept through statistics. I find it really hard. So when you look at my slides, please use your imagination on the position of the A and B, and don't take these away and use them as they are, because it's like the world's largest rubber duck, right? Like, I looked at these slides so many times and I was like, yeah, this makes sense. Now, in front of people, I'm like, audience-driven testing. I have made a terrible mistake, maybe. So, speaker rating just plummeted slightly further. She showed equations and they weren't even correct, and she didn't understand them. Worst talk ever. Okay, so the probability of B given A is the probability of A given B times the probability of A divided by the probability of B. So what we're really looking at here is not, sort of an absolute answer, because there's some probabilities involved. This is guidance for a decision. So for example, if it is cloudy, so you can see I have swapped this, I'm so sorry. If it is cloudy, do I need my umbrella? And we can feed that into the equation. So the probability of rain, given there are clouds, is the probability of clouds given there are rain, which doesn't make much sense, but we'll come back to it, times the probability of rain divided by the probability of clouds. So what we're saying here is, the question is, do I need an umbrella? And the first thing we need to look at is, how often do we get rain without clouds? The answer is not very often, but there's a thing called a sun shower, and you see it every now and then, where it's like bright sunshine, and yet it is raining. So we have that small chance. Then we multiply it by how often does it rain in the UK? Most of you will know the answer to that is almost always. And then the next question is, how often is it cloudy in the UK? To which the answer is almost always. So we can put those numbers in. So how often does it rain without being cloudy? Almost never. So 99% of the time, if it's raining, there's clouds. How often does it rain in London? I looked this up. It's about 42% of the days it rains. How often is it cloudy in London? About 43% of the days. So if you do that math, what you get is that 97% of the time, if you look out the window and it's cloudy, you should bring an umbrella. And the reason is because with those probabilities that I've chosen, almost always, if it's raining, there's clouds. So there's this really strong correlation with rain and clouds. And the likelihood of cloud is about the same as the likelihood of rain. So that means I always need to take an umbrella. I'm not sure. So the number of rainy days I was pretty confident on. The number of cloudy days I was less confident on. I sort of tried to look it up, but I think that number is wrong. I think that might be the number of days where it's like cloudy for the whole day or something. Because if you asked any of us, is it only cloudy half the time? We would say, no. That's why Trisha moved to Spain, right? So I think maybe 90% is maybe a better estimate for how often it's cloudy in the UK. And if you do that, you can see that really changes the numbers. And that's kind of exactly what we would expect, right? If we know that it's only cloudy when it's raining, if it's cloudy, we should bring an umbrella. If it's cloudy way more often than it's raining, maybe we don't bring the umbrella. And so this is the sort of the base likelihood of it being cloudy changes what decision we make when we see clouds. And so that what we're looking for is that guidance for the decision. But you can see there's sort of a problem already, which is, even just in that example I showed you, I didn't really know all of the numbers. I was able to get the rain number pretty well, but I couldn't get the cloud number. And I just made a wild guess about the sun shower number. So what do I do if I don't know like any of those numbers or that number? And this, again, when I started reading about Bayes, I looked at this formula. I said, well, I'm trying to get one number. And in order to get the one number, I have to have like 3 other numbers. That doesn't seem very helpful. That seems like actually the most useless formula ever, because I'm no more likely to know any of those numbers than I am to know the number on the left. But this is where it starts to get interesting with Bayes, which is you are totally allowed to, if you don't know any of those numbers, just guess. And the idea is that you don't know, so you're no worse off using this formula and trying to get to something that's probably going to be a better guess than you would have if you just didn't do any math and just like said, oh, I'll roll a dice and bring an umbrella. And there's another important thing about Bayes, which is not reflected in this formula. And that's that what you do is you iterate. So you take your initial belief, and then you add in new data, and then you use that to come up with an improved belief, and then you keep going round that cycle. And it's this iterative nature of improving your information, improving the quality of your answer, that makes Bayes a really powerful statistical technique. And this is quite different from something like calculating your statistical significance, where you tend to use the information that you have from one experiment and then move on to the next experiment. This idea that you're allowed to guess, and then you can make your guesses kind of better by iterating, has made a lot of people quite annoyed. So when you historically, when people were writing about Bayes, they said the study of Bayes, and in fact the whole study of probability, is just ignorance coined into science. The formula is founded on an error and must be wholly rejected. This is perhaps the only error to which the mathematical world has so deeply committed itself. And this is my favorite, a staggering falsity. So you can see the mathematicians, they were maybe a bit boring, but they get really excited about some things. And this is one of the things that they get very excited about. And it's kind of surprising, because you think, oh, it just looked like a bunch of P's and A's and B's. How could it be so offensive? But let's go through and a sort of another example where we show the iteration. So I have a billiard table, and we're going to play a game. I'm going to throw a white ball onto the table while you all look away. I won't ask you to all look away because the table chairs don't rotate and it would just be really weird. So I've got that ball. I draw a line where the ball was, and then I get rid of the ball. Pretend you don't know where the ball was, even though you all saw the slide with the ball. Now what I do is I throw some red balls onto the table. So I throw one ball, then I throw another ball, keep throwing, and I'm going to throw 5 on. And then I count up how many are on the left and how many are on the right of the line. So in this case, 2 are on the left, 3 are on the right. And now I ask you all to guess where the line is. If you imagine that you didn't know where the line was because I just showed you the line, anybody want to put a guess where the line is based on this evidence of 2 balls landed on the left, 3 balls landed on the right? Anybody want to? It's very hard to pretend to guess something that you actually know the answer to, isn't it? Yeah. Yes. So, well, I mean, that is the answer that I was hoping for. That is the answer that I would give as well. That is wrong. I'm very sorry that I made you guess, and then I told you you were wrong. It makes so much sense that 40% of your balls are on that side, so the line should be. But if you look at the maths, and if you do the Bayesian maths, what the answer comes out to, and it actually kind of makes sense when you think about it. Is 3/7 of the way across. So why is 3/7 of the way across the correct answer, when there's 2 on the left? And so we can kind of see how it works out if we do a smaller number of balls, because then it becomes more obvious that just taking that fraction isn't the right thing to do. So if I have 3 balls here, and here I have actually not shown you the line, and I tell you that 0 balls are to the left of the line and 3 balls are to the right of the line. Does anybody want to take another sort of guess of the likely position for the line after I was so rude to the first person who took a guess? Did you say 1/3? 1/5. That is very close. That is very close. Yes, that is a sensible guess. So if we used the same formula that we did to get the 2/5, the answer that we would get is 0 over 3. So we divide the number on the left by the number on the right. I think it's probably fairly obvious that just doesn't feel like the right answer, right? Like that would say the line is completely on the bumper, and if I asked you to, bet your house, you would bet your house to say we will never get any balls to the left of the line based on having thrown only 3 balls. Like you just wouldn't, right? You don't know the exact answer, but you're fairly sure that it's not 0 over 3. And the correct answer is actually 1/4. So very similar to what you said with the 1/5. And we can see this even more obviously if we do the experiment with no balls. So I have a line, I have thrown the white ball, I'm not going to throw any red balls, and I would like you to take a guess. Most people, given this complete lack of evidence, and I tell you, you have to make a bet, you have to try and guess where the line is, most people would guess that the line is about halfway across, right? Like that's, in the absence of evidence, probably half the balls will go to one side and half the balls will go to the other side. So we have this mental model of the pool table, which is that the pool table is not on a slope like that. So when I throw the white ball, it probably will end up somewhere in the middle. If I then do an experiment, and I've got 1 ball, you might update your guess. And you might say, actually, I think the line is maybe 1/3 of the way across. And then if I give you another one, you might update your guess again. You might say, oh, actually, yeah, no, now I think I'm back to thinking it's in the middle. And then if I give you another ball, you might, again, think it's sort of a bit more towards the left. So in each case, what you're intuitively doing, because you slept through statistics in university, is that you're adding the new evidence to your previous evidence, but you start with this mental model, which is the pool table is probably a normal pool table and balls, won't just all cluster at one end. And so you can see we're sort of adding it. So on our first experiment, we had 1 and 2. Then we kind of added that fraction to 1 and 3, and then we added it to the fraction. So in each case, we're just kind of adding the fractions. And that's exactly the same model that was used for that first example, where we incorrectly guessed 2/5. So we have this experiment 0. This is the experiment where I haven't thrown any balls, but I still have a pretty good idea how that pool table will behave. And then I do a second experiment where I get 2 left and 3 right. I add those 2 experiments and I get 3/7. So this technique of using that combination of probabilities, but then also starting from a guess and then iterating and iterating, and each time adding the new information that you have, is used for all sorts of modern, well, it's used for almost everything. So it's used, for example, for medical testing. If you know the success rate of a test, and you have to look at the base rate of the disease in the population before you can know how likely it is that the person you just told they have this really exotic disease actually has the exotic disease. It's used for spam detection. So spam filters tend to be Bayesian in how they detect spam. I was reading up on this for this talk, and the main thing that I learned about how they work is that people who are in the business of writing spam filters talk about spamicity, which is my favorite new word. So if you want to, bring one thing away, it's the word spamicity. Another place where Bayes is used a lot is in artificial intelligence, which brings us back to statistics in San Francisco. So, this is the classic example of using artificial intelligence for a classifier. And each time you get a little bit more information, that the person pushes the thumbs down and says, actually, no, that's not a chihuahua, it's a blueberry muffin. You update your model a little bit, and then hopefully the model becomes better and better. And apparently, actually, now 16 of 17 of these can be classified correctly with modern models. So, what to take away from Bayes? You could take away the equations. That's a lot like math. So I have another suggestion instead for what to take away, which is when you read books about Bayes analysis, they start off with the math, and then they go through and they give you more and more examples of how medical testing is, and drug testing is using Bayes, and spam filtering is using Bayes, and artificial intelligence is using Bayes, and human perception is using Bayes. And the list of things that end up being Bayesian becomes sort of almost everything in the world. So what you can do is, because everything is Bayesian, and because the foundation of Bayesian is not really having any idea what's going on at first, instead of saying, we have no idea, you can sound much more clever if you say, we are adopting a Bayesian model for this problem. And in general, as well, if you want to sort of then go to other people and say, yeah, Bayes, Bayes, Bayes. If you see statistical significance or standard deviations or that kind of thing, that is classical statistics. If you don't, and they're coming up with some kind of a probability, it's Bayesian. So let's switch topics from the happiness of statistics to talking about threads. Not that threads, this isn't a happy talk, but it's not quite that depressing a talk. Not that threads either. It's not that kind of a depressing talk. Although I'm not sure I've actually improved it. So instead of talking about threads, the nuclear war, or threads, the social media, we're going to talk about threads as in concurrency. And given the choice, I might have preferred the first two. Concurrency, it just makes my head hurt. And it turns out this actually brings us back neatly to Bayes. You remember I said everything could be reframed in terms of Bayes. So Can I blame concurrency for my headache? Given I have a headache, how likely was it that concurrency was to blame? And I can work this out by looking at how many people can cope with concurrency, how many people can do concurrency without getting a headache, combined with how much concurrency is there in the world, and how often do I get a headache in general? How many days of the year do I have a headache? And the reason concurrency makes your head hurt is partly because the amount of concurrency in the world is going up. You plug that into the Bayesian formula, and then you get a headache. So this brings us on to the next subject, which is electrical engineering, and in particular, chip design. The number of cores on your typical computer is just going up and up and up and up. So it used to be that a computer had one core. Around 2005, we got the first multi-core computer. It was very exciting. It had 2 whole cores. Now even your phone laughs at the idea of being restricted to 2 cores. We got to 48 cores about 8 years ago. We have passed 128 cores. And again, this is just, on your normal AMD Intel machine. We are getting more and more cores on these things. And so what that means, going back to the notation of probability, is that the probability of concurrency is going up and up and up just because the number of cores is going up. Why is this happening? Why would we do this to ourselves when everybody knows concurrency makes your head hurt? And the reason is because single processor performance just isn't going up anymore. It's not going up in the way we want it to. Moore's law for a long time allowed us to make a single core processor that was much more powerful than what we had 18 months ago. Now, if we want to increase the power, and of course we always want to increase the power, the way we have to do it is by going out horizontally and having more cores. The problem is that going out horizontally doesn't actually give us as much more performance as we would like. A lot of what I'm going to talk about here is drawn on seeing Sophie Wilson talk. She was one of the original architects of ARM, and she does really interesting talks on the future of computers. And one of the things she points out, which I hadn't realized, is that if you look at this curve, for a while, performance was going up a lot. So like for a while, it was going up by 52% a year. But now, performance, by which we mean the ability to solve an actual useful problem, is kind of plateauing. So our computers just aren't doing as much for us as they used to, or they're not doing as much more for us as they used to. And this is based on experimentation and history, but it actually maps really, really neatly to Amdahl's law. Because Amdahl's law says that as you increase the number of processors, your speed up does not increase proportionally. And not only does your speed up not increase proportionally, your speed up actually stops. So if, for example, I push the boat out, I invent the computer that has not yet been invented, and I've got a 32K computer, and I've got that sitting on my desk, I can only solve whatever computer problem I'm trying to solve 20 times faster than I could if I was on the 1 core. And I've got 32,000 cores. That's really depressing. So my boss comes to me and he says, this isn't good enough. We need to get more speed. Let's go up to 64,000 cores. So I've got this amazing 64,000 core computer on my desk, and I'm still only 20 times faster. I doubled the number of cores, and I got no speed up. And that was with really, really clever concurrent programming, where I had 95% of my program could be parallelized. But of course, 95% parallelizable is actually a really high bar. Probably a lot of our programs are a bit more down around this sort of 50% parallel on a good day. I think my programs are usually down around 10% parallel. So concurrency is really hard, and if we're not good at concurrency, we're not going to get the benefit of all of this hardware that we have available to us. All of that hardware is just going to be wasted, which is a shame. So really, as an industry, The hardware people have sorted out concurrency, if you count sorting out concurrency as just giving us more and more cores. The software people haven't really got to grips with concurrency yet, and this is something that as an industry we have to do. Well, when I say as an industry we have to do, the good news here is that I think not all of us have to do it. My day job is that I work for Quarkus, and one of the things that we really try and do with Quarkus is developer joy. So it is doing that engineering under the covers to make the experience of using the framework as delightful as possible. And I think with Quarkus, we're really good at taking advantage of concurrency. But I think we made a mistake in the early days of Quarkus when we described what we were doing. Because the Quarkus team are really good at concurrency. A lot of them have come from a distributed computing background. A lot of them have come from a reactive background. And they just eat concurrency for breakfast. So I made a wild guess about how many people in the Quarkus team got a headache when they tried to do concurrency. I guessed it was less than 10%. The only person I know in the Quarkus team who gets a headache with concurrency is me, so actually this number could be lower. And because the Quarkus team love concurrent programming, because they're weird, when we talked about the work that we were doing in Quarkus, we said that one of the Quarkus features, the second most important Quarkus feature, this is pulled from the Wayback Machine, was that it unified imperative and reactive. So we had this reactive core, and because we had a reactive core, you didn't have to choose at the architecture time, at the choosing the framework time, whether you wanted to do imperative programming or reactive programming. We thought this was really exciting. And I think what people who looked at it saw was reactive, 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 reactive. And then they thought, reactive means concurrency. Concurrency makes my head hurt. I'm not sure I like the idea of this. So we have redone how we describe it. It's still the same engineering. You still can do the reactive programming model if you want to, but we just know that most people actually don't want to do reactive programming because it makes your head hurt. So instead, we say Quarkus has a reactive core, and you can see this is sort of the fifth feature rather than the second feature. So it still gives you the performance benefit, but you don't actually have to think about reactive if you don't want to. So that gets you quite a lot of the way. If you're using Quarkus, it gets you quite a lot of the way because there's the framework underneath you is taking advantage of reactive principles to take advantage of the concurrency available in the processor. But what about the user code? It's probably not enough, even if we wish it would be, to just say, I have a framework that has really got good concurrency, so I can ignore concurrency in my code. Probably we still do have to think about it, all of us. The JVM, it is improving a lot in this area. So for a long time, we've had various competing reactive programming models. They were good, but they were kind of the advanced option, and I think they still are the advanced option. More recently, we've had virtual threads coming through, and that's generated a lot of excitement because what virtual threads, you could use virtual threads to have like 1 million threads. This doesn't actually solve a problem that anybody has. There's not really any benefit to this, but what virtual threads allows you to do is it makes the programming the concurrency more straightforward for a small number of threads because you don't need to be so precious about deassigning your threads. The other thing that's come through recently, of course, is structured concurrency. And again, this allows you to structure your concurrent code in a more readable, more elegant way, which means it's less likely that you're going to have some sort of horrible concurrency bug. So this is all good. And again, of course, this isn't just, it's not like there's that line between the framework and the user code. So for example, with Quarkus, we found that a lot of libraries didn't actually play very well with virtual threads. So we added an annotation so that you can just on your method say run on virtual thread, and then that just makes it quite straightforward. But we also did a lot of work with things like Jackson, for example, tends to pin on the carrier thread if you have virtual threads, which means that you're all of a sudden not getting that concurrency anymore. You're going from that 95% concurrent down to like 10% concurrent. So we've worked with them to fix that. But one of the interesting things about virtual threads is if you talk to someone who's been around for a while and you say virtual threads, usually the first thing out of their mouth is green threads. And they'll say, virtual threads, that's just like green threads. And then you go, but what happened to green threads? And they go, oh, it was a terrible idea, it failed. And then you go, but wait a minute, why is virtual threads successful and people are excited about it and green threads totally failed? And the answer is, back to that. When green threads was introduced, people didn't really need that much concurrency. Now we have so much concurrency on every single processor that we're likely to be using, we've got to get to grips with the concurrency. And so virtual threads seems like a much better idea. And there's a similar thing, for example, for ahead-of-time compilation. I used to work as a performance engineer, and people would always say, if only Java could do ahead-of-time compilation. And then I'd have to explain why that was a really bad idea. Now, it's not a bad idea. Now something like GraalVM has made this really excellent contribution. So what changed? This is meteorology. It's the cloud. When we didn't have the cloud, what AOT gave us, we didn't really need. Now that we have the cloud, AOT is solving a real problem. And we can see these sorts of changes driven by hardware lots of times. So, of course, another thing that we all need to know is my encrypted data safe? Another history lesson. When the British were attempting to crack the encrypted traffic from the Enigma machine, they had the technology to do it, but they didn't have the time because they would have to test 336 combinations of the wheel. And that would take 4 days, which, when the codes change every day, isn't really good enough. But what they were able to do is they were able to do some Bayesian analysis, and this is where a lot of this math was developed, because they were able to do things like, in hindsight, it's quite obvious that if you are looking at a message that is written in German, how many of you are German in the room? Now, for the German speakers, which is not me, does this phrase ever occur in German? No. Does this phrase ever occur in German? Yes, right? So you can see these patterns, and you can rule out some combinations quite quickly, which allows you to narrow down the search space, and that's what the Bayes is giving you. For the Enigma messages, there was an even more obvious pattern, which is that every day they started with a weather report, so you knew exactly what the first characters of the message would be. So what they were able to do was, by using that analysis to rule out some impossible things, they were able to go from having to check 336 combinations to having to check 18 combinations, which at the time was doable. And so they were able to crack the messages really effectively. Sadly for math, because this was all classified, this wasn't published until 1973, so that math wasn't available for other people to build on until relatively recently. So now, of course, having to do 336 combinations would not take you 4 days. It would take you like a fraction of a second on a modern computer. But we have larger codes now, which take more time. Can those codes be cracked? Again, this depends on what hardware we have available. And it depends on whether we have a quantum computer available. When we think about computer science, we tend to think that the most fundamental thing of computer science, if we go down to the sort of absolute bare bones, is a bit. And a bit can be 0 or 1. But if we then take that abstract computer science idea of a 0 and a 1, and we translate it to the physical world, and we go down to the lowest physical concept that we could have, which might be like the state of an atom or the state of a photon, that is not a 0 or a 1. That is a point on a sphere. And so if you imagine that your computer, instead of using zeros and ones for its computation, is using a whole bunch of tiny little spheres with all of the richness that comes from a position on a sphere, all of a sudden you have a lot more computational potential. So it means that some problems that are completely impossible to crack on a classical computer, like decrypting a really long key, can be done on a quantum computer. So quantum computers could crack most public key cryptography that's around now fairly easily. The only problem is that nobody has one of those quantum computers yet. So we're sort of in this Schrodinger's cryptography now where we kind of know they're coming. We're fairly sure they're coming, so we don't really know if our messages are safe or not, and we don't really know what we should be doing. But there are things that we can do, because quantum computers could crack most public key cryptography, but not all. So we have new algorithms that are called quantum-safe algorithms for encrypting data. And the JEPs are coming. So relatively recently in Java 24, 2 new JEPs were implemented, and they give you cryptography algorithms that are quantum safe. So that means that if you encrypt something now, and you'd really quite like it to not be decrypted in 10 years when someone has a quantum computer on their desktop, maybe, you can use the different algorithm, and your data will be safe for much, much longer. But at this point, some of you might be feeling a bit jaded and thinking, well, we've been talking about quantum computers for such a long time. We still don't have quantum computers. I am not convinced that anybody is going to have a quantum computer on their desktop in 10 years. Why is this just sort of all this hype? That brings us to our next lesson, which is venture capital. Say I have some money and I want to do something with it to grow it. I could start a baby company. And then, hopefully if things go well, I can continue to grow that company. And as the company grows, it will attract more investment. So I can go through various funding rounds. Each funding round, I will attract more investment and continue to attract more investment and continue to attract more investment. But at some point, I get kind of bored of the company, and what I'd really like my money. So what I can do then is I can do an exit. When I do an exit, the company maybe does an IPO or it gets acquired, and I get given, or my investors get given, a huge ton of cash. And the best thing about an exit is that all of a sudden, all of this work that I have to do for the company to actually run the company goes away, because the company now is someone else's problem. So I have the cash and I don't have the company. Win-win. So how do I make this cycle work? How do I attract the investment so that at each stage more money continues rolling in? What attracts investment? In an ideal world, maybe something like stability would attract investment, or maybe profit or revenue. What tends to attract investment is seeing growth in the company and excitement. Is there a narrative about this technology? Is there a narrative about this business? Is there a narrative about this area that says, this is really cool? And that's what attracts the investors, and that's what means you are more likely to be able to sell the business at a profit, which is what those investors want. And so Meredith Whittaker, who you may know as the president of Signal, she said something really interesting, because they asked her what technology she thought was most hyped. And she said, it's not that there's one particular technology that's overhyped, it's that hype cycle is actually a necessary feature of the industry. So it's not simply that one piece of technology is overhyped. It's that hype is a necessary ingredient of the current business ecosystem of the tech industry. If you have to be making people so excited and attracting that investment, that means you have to be telling them that this is really, really exciting, and it's much more exciting than anything that's come before, rather than focusing on more boring things like stability of, our business is the exact same size this year as it was last year. That just doesn't get investors excited. So, continuing on with the economics, why can't I find a job? Or if you have a job, why can't I find a new job? Why is it harder to move jobs now than it used to be? This isn't just your imagination, if this is what you're experiencing. In the US, the developer vacancies have gone quite far down. Sometimes this chart is shown without the axis at 0, which is cheating a bit, but even with the axis at 0, the numbers are really down. In the UK, it's not that bad, but there's still quite a drop. What caused this? Interest rates. In particular, we see a lot of discussion now about ZIRP, which is fun to say. So ZIRP sometimes stands for zero interest rate phenomenon, sometimes for zero interest rate policy, and sometimes for zero interest rate period. But what it basically means is that the interest rates, well, you would think it means that the interest rates are zero, given the name. What it actually means is that the interest rates are less than 1%, but less than 1% interest rate doesn't have the same ring to it. And even if the interest rate is 1%, that means that because of inflation, your money is likely shrinking. And so you can see that in the UK, we had a very long period of zero interest rates until about 2021. So they dropped after the last financial crisis, and then they stayed really low. They started to creep up again, and then COVID came along and dropped them even more to 0.1%, which is basically free money. And now they have really gone up because of inflation, shortages, war, that kind of thing. And you can see how unusual this is. If you look at the last 50 years of history, that is pretty much the only period that we've had zero interest rates. And it was 10 years, and we just got really used to it, but that's not actually the default state of an economy. And so if you look back at this investment model, I sort of drew the ideal case where you just go and you get the exit and the huge pile of cash, but of course this model has risk. Sometimes you don't get all the way to the exit. Sometimes instead, the business just collapses halfway through, and your money that you were hoping to get back instead is gone forever. So if you are making a decision about what to do with your money, and you have a choice between a software company and something like a government bond, the software company, it's got this really high risk, but potentially this massive return. The government bond, it's got a low risk, but in the zero interest rate period, it had a 0% return. So that meant that you would basically be losing money because of inflation if you put your money in a government bond. So what are you going to do with your money? You're going to put it here, where at least your money is doing something, working for you. What if interest rates are higher? That means that now, instead of having this money is not doing anything option, you could still get quite a good return here for almost no risk. And so this option starts to become much more attractive. So that means that companies get much less investment, and also companies have much less incentive to demonstrate that they're growing. Because it used to be, it didn't actually matter if you were bringing money, you just had to show that you were growing, and hiring was one way of showing that. So that meant that companies were desperate to hire. But now, with less investment, less hiring. And of course, a lot of the conversation about jobs at the moment does also mention AI. Is AI killing jobs? It is definitely the case that AI is getting a lot of investment. So I would treat with some caution some of the claims around AI, because they are part of this hype wagon. And I think AI definitely does make developers more productive, but just because AI makes developers more productive doesn't actually mean it's going to reduce the number of developers. How can that be? This is an economics principle. It's called Jevons paradox. Economics, people think it's really obvious, and they're always surprised that the rest of the world has to keep rediscovering it. So what Jevons paradox says is that efficiency improvements can lead to increased consumption. I always think of this as the highway paradox, because if you imagine when they widen the road, they add an extra lane, and they're like, oh, this road's really crowded now, but we're going to add an extra lane, and everybody's just going to sail along the road. But that's never, ever, ever in the history of roads what has happened. Instead, what happens is they widen the road, and way more people go, oh, what a cool road, let's drive on that. And we end up with a wider road and the exact same amount of traffic as we had before. And I think this is where we're going to be with software, because software is not going away. There used to be a profession. It started in the 1800s with the Industrial Revolution. People needed to turn up at the factory on time. They didn't have an alarm clock. So there was a profession that was called a knocker-up, who was a human alarm clock. Surprisingly, the knocker-up profession lasted until the 1940s. So this is a relatively recent industry. But the knocker up as a profession, there was always going to be finite demand, right? Like only some proportion of the population are going to work in the factories and need to get woken up. And as well, it's not like when you wake someone up, you can only wake them up once a day, unless it's me. You can't sort of wake them up at 10 a.m. and then come back at 12 a.m. and say, hey, do you want to get woken up again? No, they're awake. So, it's this really finite demand. But software is different. We use so much more software now than we ever used in the past, and it's just going up and up and up, because we need the software to do stuff, and then the software to do more stuff, and then the software to tell people about the software, and then the software to bypass advertisements of the software, and then it's an arms race, so then we need the software to bypass the bypassing of the bypassing, and then we need software to gamify software so we can gamify, and then we need software to monitor the software, and then we need software to debug the software, and software to manage the software, and software to write the software, and software to manage the software that writes the software. You can see where this is going, and then at some point, we need the software to try and avoid Skynet because we went a little bit too far, and then we need the software to work out the meaning of life, and there is so much software, and it's just going up and up and up and up. So I think when you look at the history of employment in our field, every time we have had a productivity improvement, the number of jobs has gone up, not down. There was a little dip in 2023 because of the interest rates, but I think the number of developers is still just going to be going up. And when you look at that vacancy chart that I showed, and you say, oh, look, it's dropped because of ChatGPT. Actually, it had started dropping way before ChatGPT. So that curve looks kind of irrelevant at ChatGPT. So I'm over time. So I will quickly wrap up the everything that I have just bombarded you with. So the first thing is that statistics is important, especially Bayes. Computers are adding more cores. That's the only way they can get more power. But unfortunately, software and humans are not very good at taking advantage of those cores. It's something our industry needs to sort out. If you want your data to be safe for 10 years, use quantum-safe crypto. It's in the JVM. It's easy. The rise of interest rates does mean a tougher job market, unfortunately. And Jevons paradox means that computer industry jobs are not going to go away despite this temporary blip from the interest rates. So with that, thank you very much. Enjoy lunch.